Namaste everyone. Welcome to NEET and JEE Mains class. We were in the 45th question in the last class. We were discussing about thermal properties. Now today we will discuss about 46th question. And it is on thermal conductivity, correct? So Namaste, welcome to everyone. Hope you are doing well. So here is the 46th one. One end of a thermally insulated copper rod, 0.8 meter long. Let me just put this in the diagram form. One end of a thermally insulated copper rod. That means it is not allowed to lose heat through radiation. It is thermally insulated. One end of the thermally insulated copper rod, 0.8 meter long. So L is 0.8, and having an area of cross section of 100 centimeters square. 100 into 10 to the power minus 4 is placed in a steam chamber at 200 degrees Celsius. Okay, here it is 200 degrees Celsius, and the other end is at 0 degrees Celsius. Now, if the thermal conductivity of copper is 400 SI units, watt per meter per Kelvin, and the latent heat of fusion of ice is so much, the mass of ice that will melt in 5 minutes. Yes. Now heat energy, so here it is ice, just melting ice is kept here. As the heat energy flows from one end to the other end, the ice starts melting. You know that the amount of heat energy required to melt 1 kg of ice is latent heat, L. And the amount of heat energy required to melt m kgs of ice is ml. So much of heat energy should flow from one end to the other if you want to melt m kgs of ice. And amount of heat energy flowing per second is without t here, right? K A theta 1 minus theta 2 into t by L. This is not per second. Per second, if you want the rate of flow, you have to bring t here. And this itself should be equal to ml, right? ml is equal to K A theta 1 minus theta 2 into t by L. So what is the mass of ice melted? Bring the latent heat of fusion to this side. Okay, we are confused with the two L's. I'll write this as L, this as L, this as L, and when I bring this L, ml, the total amount of heat energy required to melt m kgs of ice, ml. So that is equal to, I'll substitute K is 400, it's a direct problem, into, it is in SI system, area 100 centimeter square, 100 10 to the power minus 4, centimeter into centimeter, 10 to the power minus 2, temperature difference 200, that is same in Kelvin as well as degree Celsius, and the time for which it is heated, 5 minutes. In 5 minutes, how much mass of ice will melt? That is 5 into 60 seconds divided by L into L. Length is 0.8 and capital L, latent heat is 340 kilojoule per kg. 340 into 10 to the power 3, you have a kilojoule here, right? Less chances of forgetting this K because you know the actual value, 3.4, 3.6 into 10 to the power 5, something like that. So you'll get it out here, 340 into 10 to the power 3, it is kilojoules. So what is the mass of ice melted? Let us cancel as many zeros as possible, like this. 10 to the power 3 you have here, right? 10 to the power 3 means these two zeros and a 1 0 here, that is gone. So what is left with now? So we are left with 4 2s are 8. So this is 8. 4. Of course, you have a 1 0 here, 1 0 remaining. 4 2s are 8. 4 2s are 8. 8 5s are 40. 46 are 240. Correct? 240. Am I right? 4 8 40 240. Then divided by 0.8 into 34. Okay, then here 1 0 here, 2 zeros, 3 zeros, 10 to the power minus 4, 10 to the power minus 1. Hope you have followed. 1 0, 10 to the power 1, 10 to the power 3, and 10 to the power minus 4, minus 1. So this you have to divide. Okay, what may be the answer? 240. So I will write m here. M is equal to 240 into 10 to the power 1, that is 10 to the power minus 1, 24 I can write. 24 divided by 214 to 10 to the power minus 1 divided by 0.8 into 34. Okay, approximately I can find it out. This will come to, suppose if I divide this, 2 17s are, 2 12s are. Any use? Approximately again, if I divide it, or 12 divided by 0.8 into 70, that I will do. 56, 8 7s are 56, 8 1s are 8, 113, and that is 13.6. Oh, now we have to divide this somehow. Won't it be some 0.9 or 0.8 times, right? So much of, yeah, it may be 0.8 or 0.9 times, isn't it? Because if this was 13, it would have been 1. Now it is some almost equal to 0.8 or 0.9. So that much of kg. That means 800 gram. This is the closest answer, right? 800 grams, because it's almost equal. It is almost equal to 1,000. 1 kg, almost 1,000 grams. So 882.3 grams. That is that much of ice will melt in 5 minutes as the heat energy flows through conduction from one end to the other end. Okay, we will move on to the next one. 47th one. A copper rod and a brass rod having the same length and cross-sectional area are joined end to end. Okay, we will do it. A copper rod and a brass rod having the same length and cross-sectional area are connected end to end. Okay, we will connect them end to end like this, end to end, same length and same cross-sectional area. Okay, the free end of copper, okay, copper and brass, right? Yes, brass. Copper rod, free end of the copper rod is maintained at 0 degrees Celsius, and the free end of brass is maintained at 100 degrees Celsius. Okay. Assume that the thermal conductivity of copper is 4 times that of brass. That of brass we will assume 4 times that of brass, that is for copper. For copper is 4 times that of brass. The temperature of the junction is theta. Yeah, so since they are in series, the amount of heat energy flowing through both the rods must be same. So the rate of flow of heat must be same. That is Ka. So K, you have the formula Q is equal to Ka theta 1 minus theta 2 by L. Of course, if you write H, there is no T, right? It is the rate of flow of heat. So K I would write 4K. A and L gets cancelled because they are in the both sides. 4K into theta minus 0 here, because higher minus lower must be equal to K into 100 minus theta, right? Actually heat energy must flow like this. Ka by L has cancelled, 100 minus theta, theta minus 0. So Kk gets cancelled. 4 theta is equal to 100 minus theta. 5 theta is equal to 100, implies theta is equal to 20 degrees Celsius. This is the answer, right? So 20 degrees Celsius is the answer, right? Then 48. A wall has 2 layers, A and B, each made up of different material but of the same thickness. Okay, a wall has 2 layers. Okay, we'll do it like this. Wall has 2 layers, A and B. Okay, this is a wall, has 2 layers. So this is, it has 2 layers, layer A and layer B. A wall has 2 layers, layer A and layer B. A wall has 2 layers, A and B, each made up of different material but of the same thickness. Okay, thickness same. The thermal conductivity of A is twice that of B. Assume for B, this is 2K. Thermal conductivity of A is twice that of B. In the steady state, the temperature difference across the wall is 36 degrees centigrade. Total wall, right? So theta A, theta B. Temperature difference across the wall, theta A minus theta B, is 36 degrees Celsius. That is 36 Kelvin, because that is difference. Across the wall is 36 degrees Celsius. What is the temperature difference between the ends of the layer A That means if I take this as theta, you have to find out theta A minus theta. That is how much? That is the question. This difference you have to find out. Not individually what is theta A, individual what is theta, not required. What is theta A minus theta? Okay, we will do the same thing. Since they are in series, whatever the heat energy flows through this, it should flow through this also. The amount of heat energy flowing out is across both cross-sectional areas are same. That means you can write Q1 is equal to Q2. That means, you can write the temperature difference as the difference across the walls. Theta A minus theta B is 36. What is the temperature difference between the ends of the wall A? Q, again the formula, Q is equal to Ka into theta 1 minus theta 2 by L, right? Okay, L. And K, A by L doesn't have any, they don't have any role here because it is same for both, since we are equating the heat energy flowing through this and this per second. So what is the thing you have to write? K and theta 1 minus theta 2. What is K for first one? 2K. Theta 1 minus theta 2. Theta A minus theta, right, must be equal to, what is K for this one? K theta minus theta B, correct? Heat energy flowing through this per second, per unit area, per second. Theta A minus theta, theta minus theta B. This is K, this is 2K. Now we know theta A minus theta B. That's how somehow you have to bring it. So K gets cancelled. 2 theta A minus 2 theta is equal to theta minus theta B. What else we will get? Theta A minus theta B, we will bring theta A plus theta B, right? Okay. 2 theta A, to this one here, 2 theta A minus becomes plus 2 theta, plus theta B. This we will bring it here. This we will take it here. Is equal to 3 theta. 2 theta plus theta, 3 theta. But we know theta A minus theta B is equal to how much? We have 36 degrees. What is the question now? Question is theta A minus theta. So shall we subtract this? Add this. Theta B gets cancelled. When you add this, 2 theta A plus theta A, 3 theta A and 3 theta A is equal to 3 theta plus 36 degrees. Okay? 3 theta A, this is 0, is equal to 3 theta plus 36. 3 theta A minus theta, 3 theta A minus theta, minus 3 theta, 3 theta A minus 3 theta is equal to 36. Theta A minus theta is equal to 12, 36 by 3, 12 degrees Celsius. That is what is needed. Temperature difference between the walls of the first layer, 12 degrees Celsius. So that is the answer. So easy question. You have many unknowns, but you have to land at theta A minus theta, not individually theta A, theta B, etc. 49. Yeah, this is about radiation. Yeah, you know the radiation is a process, a little bit of synopsis. Radiation is a process of heat transmission where the intermediate medium is not affected. Energy from the sun, radiation from the sun reaches the earth, but intermediate medium is not affected. And it doesn't depend on the medium at all. So it is a process of transmission of heat from one place to another without affecting the intermediate medium. But when radiation is studied, we know black body radiation. Any body absorbs heat energy and it emits heat energy also at higher temperature. And all the bodies do not absorb all the radiations, all the wavelengths equally. Some absorb some wavelengths more than some other wavelengths. So they have their own characteristic wavelengths. Red glass appears red because it absorbs more green than red. It emits red, that's why it appears red. So a red glass emits red but absorbs green very strongly. Of course it absorbs blue, everything, but green is absorbed very strongly. So every object is a good absorber of certain radiation. Similarly, it is a good emitter of certain radiation. It reflects red, that's why it appears red. A red glass plate appears red because it absorbs green and emits red. Of course, not emitting, reflects red when sunlight falls on it. It absorbs green, right? So take a red glass plate and take it into a dark room. start heating it, it starts appearing with the glowing with the green color, because at higher temperature it starts emitting the radiation that it has absorbed, that is green. Green is absorbed, so green is emitted when it is heated to a higher temperature. So a good emitter of radiation is also a good absorber of radiation. So red glass is a good absorber of red, at the same time at higher temperature, a red glass plate is a good absorber of green, so at a higher temperature it is a good emitter of green. That is what is called Kirchhoff's law. Suppose you find out how much is the absorptive power of a red glass plate corresponding to green wavelength. And don't be under the impression that all the bodies are good absorber of all the radiations. No. For certain particular radiation, certain bodies are very special. As if we have human beings, we have different characteristics, right? Somebody is special in something. One may be very good cricketer, another may be good singer, another may be very good in studies, another may be very good in handling critical situations, he may be a very good leader. So something like this. So every person will have his own characteristics. So wavelength is different, that's what we say. My wavelength is different from your wavelength. I may like something else, you may like something else. So, but even in the materials, some materials when they are exposed to radiations, they absorb some radiations more than the other one. When they are heated, they start emitting certain radiation. So when they absorb, we measure it using absorptive power. What do you mean by absorptive power? It is the ratio of radiation incident on the substance, total, to the radiation absorbed. Incident in the denominator, absorbed in the numerator. The amount of radiation absorbed by the substance to the radiation incident on the substance. How much is absorbed? So if a body has an absorptive power of 0.8 means 80% it absorbs, and out of 100%, that's what. But if you compare a particular wavelength for a material, it is a very good absorber of that radiation. For example, red glass plate is a very good absorber of red, a very good absorber of green. Green and red are said to be complementary colors. And at the same time, red glass plate is a good emitter of green also at higher temperature, not at that temperature. At higher temperature, it starts emitting green. So what is the ratio of emissive power and absorptive power for that red glass plate corresponding to green wavelength? It is 1, because how much it has absorbed green, same amount it emits at higher temperature. So that is called Kirchhoff's law. A good absorber of radiation is also a good emitter of radiation. So if you have a small black dot in a china dish, you use china dish in chemistry laboratory, right? And if you have a small black dot in that, that white part of the china dish emits all the radiation, but black part absorbs. Take that china dish to a dark room, heat it, then that black part starts appearing white, because all the absorbed radiation will be started emitting. So these are all the examples. So now coming back to these black bodies are just imaginary objects which will absorb all the radiations incident on it. But as it absorbs all the radiation incident on it, won't its temperature increase? Yeah, surely its temperature will increase. As the temperature increases, it starts emitting the radiations, right? So when the black body is studied, certain very surprising things were coming out of it. That energy emitted by a black body is not the same for all the wavelengths. Certain wavelengths are emitted with more power, and certain radiations are emitted with less power. So energy emitted is not the same for all the wavelengths. So when a black body is studied, it is found that at different temperatures, it emits total energy in a different value. As the temperature increases, the energy emitted goes on increasing, and Stefan and Boltzmann put it in a law. Boltzmann law, Stefan's law. Stefan Boltzmann said that the energy, so they stated that energy emitted by a black body is directly proportional to the 4th power of its absolute temperature. It is directly proportional to the size of the black body. So energy emitted per second by a black body, what you can call power means energy emitted per second, is directly proportional to the 4th power of its absolute temperature. So I can call it as power. Power is directly proportional to the 4th power of the absolute temperature of the black body, and it is equal to, if I want to write, so this is directly proportional. Then if I want to write power is equal to, then it is sigma T to the power 4. This is energy emitted per second, And if you want it to calculate the full power emitted by a black body, you have to multiply the area, right? So area of the surface of the black body and Stefan-Boltzmann constant sigma and T to the power 4. That means, suppose the sun is emitting certain radiations, suppose the temperature of the sun is double, then the total power radiated by the sun, that is energy emitted per second and even per unit area if you calculate, and you can use this symbol as H also, then the total power emitted by the sun increases 16 times, increases to 16 times, because T to the power 4. So if the temperature of a black body gets doubled, same black body, then 2T to the power 4, the new heat energy, new radiation, total radiation energy emitted becomes 16 2 to the power 4, A sigma T to the power 4, 2 to the power 4 is 16, T to the power 4 is here, that is 16 times the original energy, because this is this one, H dash. And similarly, you can have different temperatures scales. So this is Stefan's law. Now, when this energy or the power radiated by a perfectly black body, say, is drawn for different wavelength here, distribution of energy in a black body radiation. So here the power radiated, say, when the energy radiated per second per unit area of a black body is drawn on y-axis versus the wavelength is drawn for different wavelengths. Suppose you take a black body. Calculate how much energy is coming for a particular wavelength lambda 1. What is the energy radiated totally for another wavelength lambda 2, another lambda 3, lambda 4, lambda 5. For example, how much is emitted, how much green is invisible radiation, how much green is emitted by sun, how much yellow is emitted by sun, how much blue is emitted by sun. So for different wavelengths, that is visible wavelength. So including all the radiation wavelengths, if you draw it, then the graph will look like this. That means the total radiation emitted by a black body, so here we have wavelength, total radiation energy emitted by a black body is maximum for a very particular wavelength, that is lambda m1 I call. If you go below the maximum emitted wavelength, then for this wavelength energy emitted is not as much as lambda m1, it is less than lambda m1, and it is not as much as lambda m1, it goes on decreasing. So maximum energy occurs for a particular wavelength. If you keep on observing how much is emitted, how much red, yellow, blue, green, yellow, orange, red, every radiation, visible radiation is emitted by sun, you will find that maximum energy is emitted for yellow. Yellow range is emitted to the maximum extent. So for a particular wavelength. Now take the same black body, do the experiment, find out all the wavelength emitted, all the wavelength and corresponding their intensities, that is energy emitted per second per unit area, at another temperature. Say this experiment is done at T1 Kelvin. Do the same experiment in another higher temperature, heat the black body. Now see whether each energy is emitted or not. Yes, each energy is emitted, and it is emitted more. Whatever is emitted last time, lambda m1, the maximum emission of energy for this one, that is emitted more. What about the next one? That is also emitted more. But now the highest energy is not for this one, it is for different wavelength. It is for this one, lambda m2. Lambda maximum 1, lambda maximum 2, I can write it like that. Lambda max 1, lambda maximum 2. Now the highest energy emitted wavelength, its value will be lesser than the previous value. So the maximum energy emitted is for a different wavelength which is lesser than the previous one. Now you see individually this wavelength is also having more energy, this wavelength is also having more energy now, but energy is maximum for this one, not for this one. Right? In every exam, if you go and see, observing who has scored maximum marks in the class, it is not the single person. The person to person it varies, right? So, but the person who has scored maximum value now is having lesser wavelength. So lower wavelength is having more energy now, energy per second per unit area. Increase the temperature to a further value. And remember, Stefan's law is valid here. The energy emitted is directly proportional to the fourth power of temperature. That means energy emitted should increase as the temperature is increased. Has it increased? Yes. If the area under this curve is less, that is the total energy emitted by the black body. Area under the intensity or power energy per second per unit area versus wavelength graph gives, area under that graph gives the total energy emitted. Less area here, more area here. Definitely energy emitted has been more. It should be T to the power 4. Increase the temperature further. You will find that energy emitted will be again for another wavelength. Lambda maximum 1 is here, right? Lambda maximum 1, lambda maximum 2, lambda maximum 3. Sorry, it has to be corrected. And now the highest energy occurs for another wavelength which is lesser than the previous both previous values. That means as the temperature increases for the black body, the maximum emitted wavelength, maximum energy emitted wavelength, the wavelength for which maximum energy emission occurs, its value goes on decreasing. That means I can put it in a mathematical form. The maximum emitted wavelength for which, it is not maximum emitted wavelength, the wavelength for which maximum energy occurs, its value is inversely proportional to temperature. What do you mean by that? As the temperature increases, lower and lower wavelengths are emitted with more and more energy. I think now my sentence is proper. As temperature of the black body increases, the lower and lower wavelengths are emitted with more and more energy. So lambda maximum is inversely proportional to the temperature, or lambda m into T. I'll write lambda, okay, lambda maximum into T is a constant, and that constant is called Weiens constant, and this is called Weiens displacement law. Weiens displacement law. The wavelength for which maximum energy emission occurs, its value goes on decreasing as the temperature increases. They are inversely proportional. Lambda maximum into T is a constant. That is the Weiens displacement law. So that is an important law. So Stefan's law, Weiens displacement law, and this formula for Stefan's law and mathematical expression. Important here. And one more thing here you have to follow is Newton's law of cooling. You know that rate of energy loss by any body which is having heat energy within it, and it doesn't lose the heat energy at equal rates at all the temperatures, at all the times. Hot water may cool down very fast in the initial stages, and it will not cool down at the same rate in the later stages. It cools down at a different rate at the later stages, slowly, right? If water to cool from 100 to 90 degrees Celsius takes 5 minutes, from 90 to 80 it may take more minutes because it cools slowly. So that's how Newton's law of cooling says the rate of cooling is directly proportional to the temperature difference between the body and the surroundings. The rate of loss of heat energy, that is dq by dt. Rate of loss of heat energy, amount of heat energy lost per second, is directly proportional to the temperature difference between the body and the surroundings. So this may be the surrounding temperature, which is lesser, surroundings, and this is the temperature of the body. And finally we can put it like this. Suppose a body is at a temperature T2, right? Of course you can put the equation for the constant of proportionality, and finally you can get this equation. Suppose T2 is the temperature of a hot body, and if it falls, the temperature falls from T2 to T2 minus delta T2, right? Suppose 100 to 99.5, that is the fall of temperature, 0.5 degrees. And if T1 is T is the temperature of the surroundings, okay, then T1 be the temperature of the surrounding. This is fall, right? Very small fall, so that you can take it almost T2 to T2 minus delta T2, 100 to 99.5. This is the temperature of the surroundings. Then you can have one more equation which is helpful in solving the problems. That is, I am not writing this. After solving this, you will get one equation, that is dT2, that is fall of temperature here, and there should be a difference here, dT2 divided by T2 minus T1, where T2 is the temperature of the body, almost average temperature of the body after fall, then minus surrounding temperature must be equal to a constant into the time for which it cools. You get this equation in that Newton's law of cooling derivation, right? So rate of cooling is directly proportional to the temperature difference between the body and the surroundings. That is the statement. Rate of loss of heat energy from any hot body is directly proportional to temperature difference between the body and the surroundings. What does it mean? If the body is at a very high temperature, having much difference between itself and the surrounding temperature, it will be cooling faster, right? It will cool faster, and when its temperature difference is rate of loss of heat energy, it loses more heat energy, and when it comes to closer and closer to the body room temperature, the rate of cooling becomes slower. Okay, so this is how you have to do, and when you solve the problem you will get that idea. So shall we move on to the problems now? Yes, here is the next question. Okay, right, a spherical black body of radius 12 centimeter, radius 450 watt power at 500 Kelvin. Okay, if the radius is halved and the temperature is doubled, power radiated by in watt is, so power radiated by a black body is equal to the area and Stefan-Boltzmann constant and T to the power 4. It is the energy per second is directly proportional to 4th power of absolute temperature. Total energy emitted is, this is actually H. Total energy emitted is into area. This is per se. If you want to write the equation for per unit area, of course remove area by A. Okay. Now, what are the things changed here? If the radius is halved, you know, radius should contain radius. Area should contain radius square. Why? If it is a spherical body, 4 pi r square. If it is a circular plate, it is again pi r square. Radius should be in the square form. If radius is halved, then the area becomes 1 by 4. That much is enough. Then, if the radius is halved and the temperature is doubled 16 times, correct? Because 4 t to the power 4, 4 to the power 4 is 16. Totally you will get 4 times the first power. 4 times the first power is 450 into 4, 0, 20 and 18. 1800 watt. This is the answer. Okay. So what are the things you have changed? Just I have written it. 1 by 4th, because the radius is halved, r by 2 whole square, or 1 by 4 you will get. Temperature is doubled, means 2 to the power 4, so 16. So 1800 watt. Okay. Next 50. The power radiated by a black body is P, and it radiates maximum energy around the wavelength lambda naught. Okay, we'll solve this. The power radiated by a black body is P, and it radiates a maximum energy around the wavelength lambda naught. Okay, maximum lambda naught is wavelength at which maximum energy occurs. If the temperature of the black body is now changed so that radiation maximum energy, radiates a maximum energy around a wavelength of 3 lambda naught by 4, what is the power radiated? They are mixing up Stefan's law and Weiens displacement law. Because you see, maximum energy occurs at lambda naught. Next maximum energy occurs at a lower wavelength. That means temperature has been decreased, or decreased. Because 3 lambda naught by 4 means, wavelength has decreased, temperature has to increase. It should be increased temperature for this wavelength if it has to be maximum energy. Okay, then how much is the change in the temperature? Accordingly, you can find out the maximum energy emitted, because power is directly proportional to power radiated is directly proportional to 4th power of absolute temperature. But how much temperature change occurs, that can be calculated using the Weiens displacement law. Lambda naught occurs at a time of, at a temperature of T1. Lambda into T is a constant, Weiens displacement law. Lambda is inversely proportional to absolute temperature. Lambda naught occurs at a temperature T1. And what about lambda, another lambda? 3 lambda naught occurs, 3 lambda naught by 4 occurs at a temperature T2. Because I want the relation between these two T1 and T2, which I can put it over there. What is T1 by T2? Lambda naught gets cancelled, it is 3 by 4. That means, okay, I have to write what is T2, right? T2 is equal to 4 T1 by 3. That is what I need. Second temperature is 4 by 3 times the first temperature. Temperature has increased. That's why it occurs for a smaller wavelength, 0.75 lambda naught. So temperature increases 4 by 3 times the original temperature. How much power should increase? Power P dash is equal to this 4 by 3 times the original temperature to the power 4. 4 4s are 16, 16 16s are 256, correct? And 3 3s are 9, 9 9s are 81. The new power radiated will be that much. So from Wien's displacement law, get the change in temperature. From the change in temperature, find out how much power is changed. If the temperature of the sun is doubled, radiant energy received on the earth will increase by a factor of 16, right? Increased by 16, increased to 16 actually. Okay, then 52. A perfectly black body emits radiation at a temperature T1 degree Kelvin, and it radiates 16 times this power its temperature T2. It is just the reverse of the previous problem. What is this one? So temperature must have been doubled, isn't it? If it has to radiate 16 times the more power than the previous one, temperature must have been doubled. 53. Two spherical black bodies of radius R1 and R2 and with surface temperatures T1 and T2 respectively radiate the same power, then I think it is I have not put here the ratio. I have to check it. It should be, I think, lambda 1 by lambda 2, something like this. R1 by R2. Yeah, I think we have to calculate what is R1 by R2. I think so. Let us see. R1 by R2 must be, yes, most probably so. Two spherical black bodies of radii R1 and R2 and with surface temperatures T1 and T2 respectively radiate the same power. R1 by R2 must be equal to, I have forgotten to get the equation there. What is R1 by R2? Okay. They radiate the same power, correct? If they radiate the same power, then power radiated by the first, power radiated by the second should be same. P1 must be equal to P2. If P1 is equal to P2, then what else we have? T1 is sigma A T1 to the power 4 must be equal to sigma A1, A2, T2 to the power 4. Sigma gets cancelled. Same Mustifan constant. A1 pi R1 square T1 to the power 4, two spherical black bodies, spherical 4 pi R1 square must be equal to 4 pi R2 square T2 to the power 4. Of course, I need not have written this one. They want R1 by R2. R1 by R2 whole square is equal to, I'll bring this here, this one here, T2 to the power 4, T1 to the power 4. So can you cancel one power, get the square root. This becomes R1 by R2, yes. That is what is asked. R1 by R2 is equal to T2 by T1 to the power 2, right? Because this becomes square root here, 4 by 2 is 2. So this one, yes, that is the answer. 54. The temperature of two bodies A and B are respectively 727 and 327. The ratio of heat radiated by A and B. Heat radiated by A, heat radiated by B is T1 to the power 4, T2 to the power 4, to the power 4, 273 plus 727, 273, 300, 1000, right? 273, 300, 273, 600, correct? 327, 500, 400, 600. Zeros gets cancelled. To the power 4, 10, 10. So you can cancel this, yeah. 5, 3. 27 you get. Anything? 3 3s are, it is 81. This may be the answer, correct? 81 here. 5 5s are 25, 25 25s are 625. Answer 4. 55. We'll rub this. A black body at a temperature of 2880 Kelvin. Okay. A black body at a temperature of 2880 Kelvin. The energy of radiation emitted by this body between wavelengths 499 nanometer and 500 nanometer is U1. So along this range, that means 1 nanometer range, the energy emitted is U1. Between 999 nanometer and 1000 nanometer is U2. And between this one and U3. Wien's constant is so much, then which energy is more? If you want to say which energy is more, you must know for which wavelength the maximum energy is emitted. Correct? If you want to know for which, say this is lambda 2, lambda 1, lambda 3, and energy emitted per second per unit area, somewhere here U1, U2, U1, some U3, like this. Which is more and which is less? For that you need for which wavelength maximum energy is occurring. That you must know first. Whether U1 is more, whether U2 is more, U3 is more. That means which wavelength is corresponding to the maximum energy. That can be calculated using temperature and Wien's constant. Because the wavelength for which maximum energy emitted is inversely proportional to temperature. Lambda is equal to B by T. B is equal to lambda into T, or lambda is equal to B by T is okay now for us. So lambda occurs with maximum energy for Wien's constant 2.88, okay, 2.88 into 10 to the power 6 nanometer, here we have nanometer, Kelvin, divided by, what is that, temperature, 2880, correct? 2.88 into 10 to the power 6 into 10 to the power minus 9 divided by 2880. Yeah, Wien's constant divided by the temperature of the body. So what will be the answer? This will be 1000 times, because 2.88 thousand times is 2880. So what is this answer? Lambda maximum occurs for minus 3, minus 9. 1 meter, something is wrong in the values given, then it cannot be 1 meter. So I think there is no Wien's constant, meter Kelvin, it should not be nanometer. It is only 10 to the power 6, otherwise we will get minus 3, right. This is correct. It is 10 to the power 3 minus 12, 10 to the power minus 6, yes. 10 to the power minus 6 meter. Yes. That is equal to multiply and divide by 1000. What you will get? Divided by 1000 makes it nano. So everything is in nano. 10 to the power 9 minus meters, 1000. So maximum emission occurs for 1000 nanometer. Am I right? It's correct. So here we have minus 3, minus 12, plus 6, minus 6. So that is 1000 nanometer. For 1000 nanometer maximum energy occurs. That means this is highest. 999 nanometer to 1000 nanometer U2, that is highest. For both the wavelengths it should be less, right? Because if you go to any other wavelength than this 1000, you must get lesser energy emitted. So U2 is highest. What equation? U1 0, U3 0, that cannot be so. U1 greater than U2 is wrong. U2 greater than U1 is correct answer. Because definitely it is greater than U1, because for this wavelength maximum emission occurs. Hope you have followed. First of all, find out the wavelength for which maximum energy occurs. And around that wavelength, the highest energy is occurring. Any other wavelength, energy is less. Two identical black bodies are maintained at temperatures 127, 527, direct problem, right? So what is the rate at which they emit energy? H1 by H2 is equal to 127, 520, you have to convert it into Kelvin, 127, 273, 300, 500, 400, 127, 273, 300, 400, 273, 300, 800. That is 1 by 2 to the power 4, 1 by 16 times. Yeah, this is the answer. 1 by 16 times the energy emitted. Ratio 57. Newton's law of cooling. Yes. Certain quantity of water cools from 70 to 60 in the first 5 minutes and 54 degrees Celsius. This one. 54 degrees Celsius in the next 5 minutes and 254 degrees Celsius. 70 to 60 in the first 5 minutes and 254 means 60 to 54. 70 to 60, 60 to 54 in the next 5 minutes the temperature of the surroundings is. So if I write the temperatures like this, 70 to 60 first of all, and room temperature is somewhere here, right? So room temperature you have to find out, T. Then 60 to 54. Now when you want to write in this formula, dT2 fall by T2 minus T, T is the temperature of the surroundings, must be equal to some constant into the time for which you are cooling it. But when you write this temperature difference between the body and the surroundings, should I write when it cools from 70 to 60, 70 minus T or 60 minus T? Temperature difference between the body and the surroundings. Should I write take this difference or this difference? You take the average difference, 65. 70 plus 60, 130 by 2. This is average. Average temperature, that we will take it as T2. So now we will substitute. That implies for the first fall, 70 to 60, what is dT2? It is 10. So dT2 is 10 degrees Celsius divided by T2, average of this 65, minus temperature of the surroundings, T, that I don't know, is equal to, actually this is loss minus K, loss of heat minus K into time for which it is heated. Let it be in minutes because we are going to write another equation. There also we will maintain the minutes unit and then we will cancel it. Equation 1, then, yes. What about the next one here? What is dT2? dT2 is here 6 degrees Celsius and average 60 plus 54, 114 by 2, it is 57. Yeah, write the equation for this. I will write the equation here. Okay, this is T. Okay, write it here. dT2, that is 6 degrees Celsius divided by average is 57. Temperature difference between the average temperature and the body of the surroundings is equal to minus K in the next 5 minutes, equation 2. Now both the right hand sides are same. Both the things are happening in the 5 minutes. So let it be equated. You can divide it, right hand side becomes 1, or you can equate it. 10 by 65 minus T must be equal to 6 by 57 minus T. 2 5s are, 2 3s are, cross multiply. 5 57 times 35, 28. Minus 5T is equal to 3 into 65, 195 minus 3T. Okay, so we will write the next step. Shall I write the next step here? 285 minus 195, that's better. 285 minus 195 is equal to minus 5 to that side, 5T minus 3T. This is 550, 195, 5 and 180, 185, 550, 89, yeah, 190, correct? 285 is equal to 2T, T is equal to 190 means it is 95, no, simply 90 it is, not 190 because, yeah, 95, 5, 200, 85, 90, yes, 90. T is equal to 90 by 2, that is 45 degrees Celsius, right. We have a similar question. A body cools from 50 degrees Celsius to 49 degrees Celsius in 5 seconds, okay. The temperature of the surrounding is 30 degrees Celsius, okay. The time taken by it to cool from 40 to 39, yes. Grab this, similar one. This will give you the idea in which you have to work out the problem. A body cools from 50 to 49, 5 seconds. And it cools from, temperature of the surrounding is 30, okay. How much time does it take to cool from 40 to 39? Here average is how how much time? Average is 39.5 between the surroundings if you want to take. Here 49.5 is the average. And here dt2 is fall is 1 and here dt2 fall is 1. So we'll write formula dt2 by T2 minus T1 or T2 minus the temperature of the surroundings must be equal to some constant minus into time for which it is heated, cooled, time for which it is allowed to cool. First equation dt2 1 divided by T2 minus T, 49.5 minus T, average temperature minus T is equal to minus K into 5 seconds. One equation. Second one, from here to here, fall. dt2 1 divided by 39.5 minus T, 39.5 minus T must be equal to minus K into how much time is taken. Oh, this is given, 30 is given, right? 49.5 minus 30, temperature of the surrounding is given, 30 is given. You have to find out what is T. So shall we divide it? 1 by, of course, what is this? 49.5 minus 30, it is 19.5. What is this one? 39.5 minus 30, 9.5, isn't it? 39.9.5, 19.5. So 1 by 19.5 into 9.5 by 1 is equal to 1 by 19.5, 9.5 by 1 is equal to, 5 divided by T. Is it okay? 1 by 19.5, 9.5 by 1, so that becomes ulta, 1 by 9.5, okay, then it is here, this one is, I think we have gone wrong, 1 by 19.5 here, so 5, yeah, right, T, yes. Now, can I take it almost equal to 9.5, 2 times is 19, right? 19.5, 2 times, almost 10. That is the only nearest answer you have, 10 seconds, enough. Nearly equal, is it written? Yeah, nearly, okay, time taken, near time actually, almost 10 seconds. Okay, 59. A metallic sphere and a metallic disc, one is disc, another is sphere, are having the same radius, same metal. That means same metal means nature is same, right? So metallic sphere radius is same as, okay, a metallic disc like this, say, of same radius. If they radiate, they are heated separately at the same temperature T and allowed to cool in the same environment. The ratio of their rates of cooling is, yeah, rate of loss of heat energy. How do they emit radiation? And you know, it is directly proportional to surface area. They are made up of the same metal. And you know that heat energy is directly proportional to area, which is directly area. So heat energy emitted, ratio of their rates of cooling, H1 by H2. It is surface area here 4 pi R1 square, and here you can take it as two surfaces. One is here and another is the lower one. It is 2 times pi R square. One area, another area, 2 areas. So ratio of their rates of cooling, right? The rate at which heat energy is emitted is directly proportional to the area, 4 pi R1 square and 2 into pi R1 square, it is 4 pi R1 square. So it is 1:1. Is it 1:1? It is 2:1. Okay, 2 into pi R squared, 4 pi R squared. 4 pi R squared is the surface area of this. Have the same radius, they are heated separately to the same temperature T and allowed to cool in the same environment. The ratio of their rates of cooling is, rates of they are heated separately, there are 2 areas, pi R1 square, 4:2, right, here, yeah, answer is correct. This is 2:1. I'm thinking this is also 4 pi R1 square, so 1:1 I'm thinking, so answer is correct, 2:1, that is the answer. 4 pi R1 square, 2 pi R1 square, so 2:1, yes. Next problem, because the amount of radiation emitted or heat lost is directly proportional to the surface area which is exposed to the environment, surrounding temperature. 60. The maximum wavelength of radiation is emitted at 2000 Kelvin and emitted radiation for wavelength of 4 micrometer. What will be the maximum wavelength emitted at 2400 Kelvin? Yeah, lambda m into T is a constant. Lambda m2 into T2. That's all. Wien's displacement law. The maximum wavelength of radiation emitted at 2000 Kelvin is 4 micrometer. What is the maximum wavelength emitted at 2400 Kelvin? 2400 Kelvin, lambda m2. It is 2000 into 4 divided by 2400. That is the maximum wavelength emitted for the second temperature. 2 zeros gone, 4 6s are, 4 5s are. 20 divided by 6 is lambda m2. This is 3.33. Of course, everything is in micrometer. This is the answer. So that is about Weiens law. Yeah. So that is about all the questions here. 60 questions we have finished, right? It is 60? Yeah. Yeah, 60 questions. And we will move on to thermodynamics, which is a very important part. We will solve some questions in the next class in thermodynamics, the graphs and thermodynamic processes and that heat engine. So they have some interesting questions. You will have more questions, especially for NEET, right? And also for JEE. So especially graphs. So we will meet in the next class. Thanks for watching my class. We will meet in the next class with lots of questions. Till then, take care. Thank you.